Hello, my name is Raz Youssef, and I'm going to go over the hands-on demonstration part in ZBridge. The goal of this demonstration is to let people experience the process as a whole while watching the results in every step of the way. We will use a Solibri viewer, which is a FreeIFC viewer, and Gygax, which was developed under the ZBridge project by Philip at the University of Cambridge. We will use them to experience every step of the way. As you can see on the first page, we have the 5 main stages of ZBridge connected by the actions needed to reach that stage. The first stage requires laser scanning and high resolution photos of a bridge, and the rest of the stages are made automatically by computers. So first, we worked on a couple of bridges. A few bridges from Cambridge, England, a bridge from Haifa, Israel, and a few bridges from Atlanta in the US. We can see pictures here of a bit of each bridge. You can also see where we put scanners to scan those bridges. This is a scanner. This is the Haifa bridge. It's a girder bridge. And this is some of the Atlanta bridges we used. Laser scanner results, or photogeometry, are exported as point clouds. The point cloud represents the surface geometry, but doesn't have any other information about the points. You can see a few of the point clouds from Cambridge bridges, the Haifa bridge, and the Acworth bridge from Atlanta. Now let's open a point cloud that was generated from the Cambridge scan with Gygax. As you can see, the scanner catches more than just the bridge itself. We capture plants, trees around, vehicles, people walking around. Also, we can see that there are places who are less dense than others. You can see, for example, here that we almost have no points generated. That's because this is the place where the scanner was actually placed. So, for example, the surface beneath it was not captured. We might also have elements that are obscured by other elements, so we miss part of them on the scan. But as a whole, this is the point cloud, and from this we want to generate actual geometry. So after we got the point cloud, we're using specialized algorithms to cluster points and identify surfaces, and then we associate surfaces together to identify objects and rebuilding solid objects. Now, as I mentioned in the point cloud part, objects might be incomplete due to occlusions that we will see in a minute. So this part is purely geometry generated from the point cloud. We don't have any information on the objects. In our research, we focused on the main elements of the bridge, but you can potentially do the same for any parts of the bridge, like the railing and so on. Let's have a look at some of the 3D geometry generated. This is Cambridge bridges, and this is the Haifa one. We will open them in Solibri and look at them. So this is the slab bridge generated from the algorithm. Now remember, we don't really have any information on every object yet. We just see the geometry. And this is the Haifa bridge generated. Now, as you can see here, the geometry generated from the point cloud is not perfect. We have gaps here between the objects, and we also have beams or girders that are not in the real size of them. The reason for that is that the laser was the laser scanned from around this place, so those objects are included for him, so we couldn't generate the whole points from it. So we have a 3D geometry which is not perfect, and SimBridge will attempt to repair it in an automated way. We can also see that we don't have real information about every object here except the geometry. If we select one of the objects, then you can see we don't really know what it is. It's just a beam. Also, all the objects are together as just geometry. We don't really know any information about them yet. Just geometry. Now, after we generated the 3D geometry, we are using enrichment tool to discover information about the objects and creating an actual beam model. So this semantic enrichment step, we take physical objects and turn them into logical objects by classifying them, numbering, and aggregate them into various ways. We also try to fix the occlusions that happened as a result of the missing points in the scanning. So by the end of this process, we have a beam model, which is actually a model with the information that is useful. Let's take a look at one of the 3D geometry examples we saw previously and the results after the semantic enrichment. So here we have the enriched file of Haifa Bridge, the beam model. Again, this process is automated and the input is the 3D geometry file. So after the semantic enrichment process, each element is classified. You see, this is a primary girder, deck slab, this is a transverse beam. Now, it also creates aggregation for some elements into different systems. So we know the lighting system contains the two lighting fixtures here. The subtractor contains all the columns, and so on. It also creates non-physical elements that represent certain information. For example, in this bridge, we create spaces which represent the spans on the bridge. Now this information is used by all kind of professionals like bridge inspectors, so SimBridge can deduct extra information that helps them. Now let's look at some of the occluded beams that we saw in the 3D geometry. Now here we can see this is the old beam and this is the new one. So SimBridge managed to find those beams who were shortened and fix them. And here we can see all the new geometry generated by SimBridge. We also generated a grid for the model. As you can see here, based on the rules we created, we numbered the grid that fits the model and provide us with more information to be used by bridge inspectors, for example. Let's look at another bridge. This is a slab bridge, was enriched by the semantic process. Now you can see this is also filled with information. This is a column, and we also number those columns, or all the objects. You can see this is column 1-1. Here we have a deck slab, which is 2, 1. Underneath it we have a bearing with numbers as well. So we have numbered the elements as well as classify them here. So now that we have the BIM model, which is a model filled with information about the elements, the next step is to detect defects on those elements. So this step is taking a BIM model and using a very high resolution pictures, attach them to the elements. The defects can be viewed as if they were at the bridge and close to its surfaces. And you can use this information to assess damage and repairs and more. Thank you for watching.